In this video I am going to discuss about several important problems on real analysis. As you can see, I have listed few questions and I am going to discuss about its solutions. All these problems are very important for your upcoming examination, so please listen carefully and observe carefully. So let us start with the first question. A certain set S is given here. Say the structure of S is 3 to the power n plus 1 by 3 to the power n. Obviously n is a natural number, and you have to show that it has no limit point, and also we have to justify whether it contradicts the criteria of Bolzanov-Weierstrass theorem or not. So first of all, remember the criteria of Bolzanov-Weierstrass theorem or statement of Bolzanov-Weierstrass theorem. Every bounded infinite subset of R has at least one limit point. So first of all, if you consider the set S, here you can see if you put different values of n, then definitely you will get several elements corresponding to S. That means the given set S must be infinite. And also you can see as n tends to infinity, the structure is also tending towards infinity. That means the structure is what? Unbounded. So technically you cannot have any limit point, but here you can understand the absence of a limit point does not contradict Bolzanov-Weierstrass theorem. Why? Because every bounded infinite subset of R has at least one limit point, but here the structure is not bounded at all. It is an infinite as well as unbounded structure, and hence we can write, because S is infinite and unbounded, so technically the theorem does not holds good for this particular expression or particular set. That's why finally I have written as S is infinite and unbounded, whereas the theorem holds if it is bounded and infinite. So practically S represents an infinite set, but because it is unbounded, it is not necessary that Bolzanov-Weierstrass theorem should be true for this one, and hence it does not contradict Bolzanov-Weierstrass theorem. This is the result of the first one. Now also I have given a note that the conditions of Bolzanov-Weierstrass theorem, here you must note that I have written in short BW theorem, but you should not write in examination like this. You have to write properly Bolzanov-Weierstrass. It cannot be denied, or you cannot omit the conditions. What are the conditions? The set must be infinite. You cannot drop this condition because you all know in case of a finite set you cannot have any limit point. For instance, you can understand if you consider any finite set and if you choose any element from it, and if you want to find out the neighborhood of that point, then within that neighborhood you cannot justify that there exists infinitely many elements, whereas we know neighborhood of any particular point belonging to a set should contain infinitely many points, but practically it is not possible for a finite set, and hence the condition of infinite structure should not be omitted. Similarly, the second condition, that the set should be bounded, is also essential for the criteria of Bolzanov-Weierstrass theorem, because if you consider infinite unbounded set, then you can see, for in case of natural number, in case of set of integers, you cannot have any limit point. For instance, if you write the elements of natural numbers 1, 2, 3 and so on, then you can consider the general structure of that set as n. Because n tends to infinity, it will be unbounded, and hence you cannot have the criteria of getting a limit point, and consequently you can say both the conditions for Bolzanov-Weierstrass theorem, that is infinite as well as boundedness, these two are very essential in order to justify this theorem. Now we have a very important theorem which states that we have to show that the derived set of any bounded set must be bounded. That means technically you can choose any bounded set S, so that as you have claimed that the set is bounded, you can choose suitable real numbers h and k such that S is a subset of closed interval h, k. Now in order to prove that the derived set is also bounded, I have written, in order to prove this result, it is sufficient to justify that whenever we are considering that there does not exist any element of S dash, obviously you can understand what is the meaning of S dash. S dash is nothing but the derived set of S. It should not be less than what? H, and it should not be more than k. So actually we are trying to justify there does not exist any element which is less than h, and it is also greater than k. Now for your convenience, I have drawn a rough diagram, as you can see here. Here I have drawn, let me show you the figure properly, otherwise you may not understand. Here you can see I have drawn line diagram. Obviously in this line diagram you can understand a certain interval h, k is shown, and there exists a point which is lying outside of this interval. So as per my diagram, p is greater than k. Now again you must remember, you should not show this type of diagram in the examination, but it is for your own understanding. Now let us consider a certain element P, as I have shown, which is greater than K, satisfying this criteria. Obviously P is greater than K, so that means there is a distance between P and K, so P minus K must be positive. Now we can choose epsilon, which is sufficiently small, greater than 0, can be taken as P minus K. So technically this particular difference has been chosen as epsilon. Now we can select this particular element epsilon and we can create a neighborhood corresponding to P, so that will be P minus epsilon and P plus epsilon. Technically this neighborhood of P contains no element of h comma k. As you can see from the second diagram, here I have drawn the neighborhood corresponding to P, whose endpoints are P minus epsilon and P plus epsilon. And also we can say, as S is contained within this closed interval h comma k, so it does not contain any element of S. That means in this case you can say P is not a part of S dash. Now here we have shown this criteria whenever P is greater than what? K. Similarly we can show this criteria whenever P is less than H. That means whenever P is less than H, then also by similar argument it can be shown P is not a part of S dash. Now we can take the help of contrapositiveness. So contrapositively we can say, if P is a part of S dash, then P must belong to H comma K, but P is taken arbitrarily. So here we can say all possible limit points of S should lie within the interval H comma K closed. But we know the set of limit points is known as what? Derived set, that is S dash. So S dash is a subset of what? H comma K. But because H comma K itself closed and bounded, so we can say anything which is contained within this closed and bounded set definitely behaves like a bounded structure. So S dash is also bounded. So whenever the original set S is bounded, its corresponding derived set is also bounded. So this is the proof of this theorem. Now we have another important result. The closure of a set S is a closed superset of S. I hope we all understand what is the meaning of superset. If A is contained within B, then A is the subset, B is the superset. That means larger one is the superset, smaller one is the subset. So let us use the definition of closure. Closure means what? S bar. Suppose this is the closure of S. S bar can be written as S union S dash. So definitely S dash is nothing but the derived set of S, and as you can see, S bar comprised of two different sets, S and S dash. So technically S must be a subset of what? S bar. And so in other words you can say S bar is a superset of what? S. Now we have to show S bar is closed, and to prove this one, let us use the concept of complementary structure. That means if we can justify R minus S bar is open in R, then our result will be justified, because the complementary structure of S bar is open. That means the original structure must be closed in R. So let us take any arbitrary point P taken from R minus S bar. Now obviously R minus S bar is the complementation of S bar, so P should not be a point of S bar. Now for your own convenience, you can imagine this type of diagram. Here you can see this is the total real number system R, of which one part is denoting S bar. S bar is S union S dash. I am choosing one particular element P. As you can see, this is that particular element P taken from R minus S bar. Let us create an open interval, that is the neighborhood corresponding to P, that is P minus epsilon comma P plus epsilon. And also you can understand from this figure, it does not contain any point of what? S. So if I want to take any arbitrary element, say Q, as shown in the figure, it is totally different to that of S. So whenever Q is a part of this neighborhood, it should not be a part of what? S bar. So that's why I have written the same thing. Whenever Q belongs to this open interval or in this neighborhood, Q contains no points of S, and also it is not a part of what? S bar. But you have taken Q in an arbitrary fashion. That means no point belonging to this interval is a part of what? S bar. So if it is not a part of S bar, so from the figure on also analytically you can say it should be a subset of what? R minus S bar. That means you have taken an arbitrary element P, and R minus S bar is behaving like what? A neighborhood of that particular point P. So technically each and every point belonging to R minus S bar is as if looking like an interior point. So R minus S bar must be open, and hence its complementary structure, that is S bar, must be closed, and hence you can say S bar is a closed superset corresponding to S. And closure of any set is closed. That's why we can understand it should be a closed superset. Now to prove the next one, we can take the help of this proof. the closure of a set S is the smallest superset of S. Already in the previous theorem you have seen, we have proved the closure is a closed superset of S. So for short question you can write in this fashion, but for broad question you have to add the previous theorem also. So here you can see, as we have mentioned, that we know that S bar is a closed superset corresponding to S. Now in order to compare whether it is smallest or not, we have to consider any other closed superset that is also containing S. Suppose that one is T. So T is another closed superset such that S bar is a subset of T. Now T is closed means R minus T, that is complementation must be open, and hence you can say T is a closed superset of S. So R minus T, which is complementary structure to that of S, must satisfy the criteria R minus T intersection S should be equal to phi. You can also imagine this type of diagram. This is the real space R. You can say you are choosing any particular set S, as if you are considering this one. Now T is like this. So if we exclude this region, that will be what? R minus T. So you can obviously understand R minus T has nothing to do with S. This smaller part is S and this part is what? T. So that's why we can say R minus T intersection S should be equal to phi. Again I will say this type of diagrams are for your own understanding. You need not to draw all these things in your examination. So if R minus T intersection S equals to phi, so this ultimately indicates that R minus T has no point which can behave like an adherent point, and so obviously only one possibility is there, S bar should be a subset of T, and that is our required criteria, and technically we can say the result follows. And then I have written a very important result. I haven't proved this one in this video because it is already given in any standard book. A set is closed if and only if S bar is equal to S. So you all know this proof, and this one is also a very important result for your examination point of view. Now moving on to the next result, let us consider the next problem. Now let us shift our attention towards the compactness. This is another important section for your real analysis examination. A is closed and B is a compact subset of R, then we have to show that A intersection B is what? Compact. So B is a compact subset of R. Definitely it is closed and bounded by definition of compactness. A is closed, and that means A is closed, B is closed, and we are considering the intersection of two closed sets, but it is also a closed set as per basic theorem or basic property of a closed set. So A intersection B is closed, it is already confirmed. Now A intersection B means what? Just follow the definition from set theory. It should consider all possible common elements of A and B. Because B is bounded, because B is compact, so we can say B is closed and bounded. So it follows A intersection B is also bounded, and hence already it has been justified that A intersection B is closed. Now we have said it is also bounded. So intersection B is closed as well as bounded. That means it is definitely a compact subset of R. So this is the proof that A intersection B must be compact in this case. Now we have another important result. Can we justify whether the set of natural numbers is a compact set in R or not? So for that purpose, let us imagine any natural number n is taken, and we are considering a certain open interval n minus half comma n plus half. That means if we choose n equals to 1, 1 minus half comma 1 plus half. If we choose n equals to 2, 2 minus half comma 2 plus half. This type of open intervals can be drawn. Now we can say this is nothing but a particular open interval which can contain the elements of the type n. So in this way, for different values of n, we can have different possible open intervals, and collecting all such open intervals, we can consider a new collection that is given by F. So that's why we have started our answer from here. Let us consider a collection F, n minus half comma n plus half, which is an open cover corresponding to n, and every natural number, as you can see, it is properly contained within this particular open interval. But the problem arises if we follow the definition of compactness. We know open cover can be drawn or it can be created as per your convenience, but you have to justify the existence of finite subcover. So here it is impossible to construct the finite family of this type of intervals that can consider all possible natural numbers, because the set natural number itself is what? Infinite. So that's why I have written, but a finite number of open intervals cannot cover the entire natural number system, because many of the natural numbers should lie outside the union of those of that particular finite number of open intervals like this. So that means you can create an open cover. However, you failed to justify the existence of finite subcover corresponding to that open cover, and hence you can say the set of natural number cannot be justified as a compact set corresponding to the real number system or compact set in R. Again, let us consider another problem. This problem also came in your examination. Already in the previous year's question you can find this one. So a is equals to 1,7/2 closed interval, b is equals to 1,9/2 open interval. We have to justify whether a intersection b is compact or not. So first let us define the two sets. First, I have claimed that a union b is not a compact set. Why? As you can see, if you choose any element from a, it should lie between half and 7/2. So definitely the set is bounded. By similar argument, you can say if we choose alpha taken from b, then alpha must lie between 1 and 9/2. So here it is also bounded, no doubt about that. That means a and b, both of them are bounded. So union of two bounded set, that is also bounded. But the problem arises here, 9/2 can behave like a limit point. So if you take the union of a and b, 9/2 is not contained within that structure, because 9/2 lies on the right extremity of an open set. So or better to say an open interval. So 9/2 is not a part of a union b. And if you remember the definition of closed set should contain all possible limit points. So here 9/2, which is acting like a limit point, but it is not a part of a union b. So we can say union b cannot behave like a closed set. So although a union b is a bounded structure, but it is not a closed structure, so it cannot be compact. So here you can say the final result is that A union B is not compact in this circumstance. Now we have considered a certain important short question from the series summation un square, summation vn square. Several times I have mentioned in the classes that if we consider the summation, then we have nothing is mentioned that the summation should vary from n equals to 1 to infinity. Given that these two structures are convergent, we have to prove their product summation un vn, that is also convergent. Here you can say that summation un square and summation vn square both are convergent. So half of the summation of un square plus vn square is also convergent, and consequently you can understand un square plus vn square by 2 within summation, that is also convergent. Now let us choose two distinct quantities, just like algebraic quantities, un square and vn square, and applying am is less than what? Gm. Then you can say just root over ab. So here it will be root over un square into vn square less than a plus b by 2, that is un square plus vn square by 2. Ultimately it will show you un vn, you are taking the positive square root, less than half of this expression. Just taking summation on either side, you can see the right hand series, which is larger than summation un vn, shows that the right hand part or the larger part is what? Convergent. So just apply the concept of comparison test, and hence you can say by comparison test this part is convergent, and hence summation un vn is also convergent. But however, you can consider this note also. If we consider un square to be a convergent structure, then it is not necessary that un is also convergent. For example, we can choose the familiar structure un is equals to 1 by n and un square is equals to 1 by n square. Here you can see un square summation is summation 1 by n square, which is a standard p series form with p is equal to 2 greater than 1, and hence it is convergent. But if we take summation un, that is what? Summation 1 by n, it is the harmonic series, and you can also say it is a p series with p is equal to 1. So in this case it is not convergent at all. So it means if summation un square is convergent, you cannot say that summation un is also convergent. So this note is also very important. Now another important short question from your examination, previous year's question. Suppose we want to provide two distinct sets and such that their interiors are identical. It's very easy. You can consider a certain semi-open or semi-closed structure A and B. say I have given 1 comma 2, 2 is open in this case, in the second case 2 is closed but 1 is open. So interior of A and interior of B in both the cases, you can understand, can be taken as 1 comma 2, because the interior portion is nothing but all possible points which are lying inside this interval. And also you can say that A and B, these two are in terms of characteristics they are different, so that means we have created two different sets where A not equals to B, you can say, but their interior is such that we can say interior of A is equals to interior of B. Now here I have given another note that sometimes it may be asked in your examination, give the example of a set whose every point can behave like a limit point. You can choose any closed interval like A comma B. Here I have given one such example. Suppose we want to take 1 comma 2, then every point of this closed interval can behave like a limit point. So this is again can be considered as an important short question. Also I have given another note where I have shown that this particular set S can be considered neither open nor closed. Suppose if you are asked to give an example of a set which is neither open nor closed, then you can take the help of this example. And finally we have the last question for today's video. The closure of a set S is the intersection of all closed supersets of S. So here it is not mentioned how many closed supersets of S should be taken, so that's why it is better to consider a family. And whenever there is a family in real analysis, we all know definitely there should be an index set. So F is supposed to be the family of closed supersets of X, and we are considering F contains all elements of the form A lambda such that each and every A lambda contains S, because they are all supersets corresponding to S where lambda belongs to index set capital lambda. Now suppose if we take the intersection of A lambda, then we get the smallest member of this family, say that is T. Now we want to justify that closure of S, that is S bar, should be equal to T. Now S bar already we know it is also a closed superset of S, and S bar because of this property must be a member of F, because F contains all possible closed superset of S, so S bar is a part of F. So T is the smallest possible member of F as per our construction, because T is nothing but the intersection of A lambda. So you can say T can be considered as a subset of S bar. But again, T is also the intersection of a family of closed set. So that means T itself closed. So it is also containing what? S. So you can imagine the situation like this. S is a member of S bar. By virtue of our construction, S is also a member of what? T. So S is a subset of S bar, ultimately implies S is a subset of T. So combining these two, we can say S bar is also a subset of T. So finally, just consider this is equation 1, this is equation 2. You can say from 1 and 2, definitely S bar is equal to T. So this is the proof of this particular result. So this result is also important. All these short questions are very, very important. And finally, I have given a note. You also know this proof. If S is bounded, then S bar is also bounded. Now I will suggest all of you to go through this video very well, because some questions may come in tomorrow's examination, and obviously each and every problem is very important. So please listen carefully and observe each and every solution carefully from this video. Thanks for listening and thanks for viewing.